2, 1. So here's an example of charges which are in 2 dimensions, and what we want to be able to do is we want to apply Coulomb's law, okay, which is right there. And what I want you to try to think about is if we have, so this D, okay, which is in the actual diagram, I'm going to set it equal to 1 centimeter. Okay, so for that purpose. And our goal is going to be to try to find out what is the force, the electrostatic force on Q2, which is coming from Q1 and Q3. So notice that all of the charges are given here, right there, and we want to be able to find that out. Now this is going to lead us into, as you will see, kind of a 2-dimensional diagram, okay, so that we will have. However, because the distances are the same, you'll notice that this actually shouldn't be a very difficult problem in order to be able to solve it, okay? So, but we'll see what's going to happen. All right, so first of all, if we want to be able to find what the force is on Q2, so we're going to use superposition. So I'm going to first find out what the force between these two are, okay? And then what the force between these two are. Now, notice that because the distances right here, okay, are all the same, then really, okay, we're going to be just finding out one of these forces, okay, that we need, because the other one, at least in magnitude, is going to be the same. The direction might be different, okay, because as you can see here, so this one is negative, okay, of the Q2 and Q1. All right, so let's kind of get started. So step number 1, I'm going to find what is the force on Q2 coming from Q1, and that is going to be equal to, so we're going to take Coulomb's law, so this is going to be the Q1, okay, and Q2 charges divided by whatever the distance between them is. Now, so this is the, well, I mean, is it a tricky part? It's not really a tricky part, but we do have to find out what that distance will be, because notice that this r squared, which is really the distance in between these two. So if you were going between one and the other, so this is that distance right there, right? So that's what we actually need. So we're going to have to use, you know, the Pythagorean theorem. I mean, it's not that difficult in here because the D is equal to 1 centimeter. So as you can see here, so I'm going to call this, you know, my, you know, D right there. Okay, so let me just kind of change it back in here. So I'm going to call this D. Okay, so let's say D bar. Now, once I find that, I will also know what the distance between here and here is, because that's going to be the identical distance, right? So these two are actually equivalent. And so that's why those two actual forces are going to be the same, just directions might be different. All right, so let's take a look and see. So let's find out this D. Well, so that D, okay, basically comes from the triangle, okay? So as you can have it right there. So that's going to be the D and the D. This is the that. Okay, so this is the hypotenuse right there. So we know that the squared is going to be equal to, now these are 1, right? So this is going to be 1 squared plus 1 squared, which is just 1, which is just going to be equal to 2 altogether. And we're going to take the square root of that. So that's going to be the distance, and this is in centimeters, right? So this is what we have right there. So now don't forget, if you want to change it back into meters, you're going to have to divide by 100 centimeters or just move it by the prefix, okay, right there. Okay, so now that we have it, okay, so I'm going to kind of go back in and punch everything into the calculator. So I have my Q1, I have my Q2, so notice these two are equivalent to each other, so they're both equal to this. So what does that tell me? Well, so that tells me that the force must be a repellent force, okay? So basically it's repelling each other. So I have, okay, I'm just not going to complicate this diagram any further. So I'm going to kind of redraw this, okay, right there, so that just you can see it. And I'm going to scale it upwards a little bit. So this is my charge that I have right there. So that's the charge that I'm looking for. So therefore the first force is going to be, okay, in this direction. All right, so it's going to be in exactly the same direction that I have there. Okay, so that is coming, basically just drawing this right here. okay? And that's the force that I have, and this is coming from right there. Now, I actually will know exactly, okay, what the angles in here are, right? Because of the fact that this is D and this is D. So since these two are the same, right, that you have this, I mean, you can use your trigonometry, okay, which is opposite, okay, over adjacent, right? But these are equivalent to each other. You'll find out that this is 45 degrees, which therefore means this is 45 degrees, and therefore this is 45 degrees because it has to make a 90. So that's going to be nice because we're going to know exactly, okay, what that component is. Okay, so I'll come back to that. So let's do the calculation. So I'm going to take out the calculator and punch it in. All right, so now I have what my force is. So let's say this is 64.728 okay, newtons. So I'm not going to round anything yet. Okay, so this is how I'm going to just leave it. So now I have this particular force, and that is that first force, which is this one, which is coming from Q1 onto Q2. So please remember, we're trying to find what the force is on Q2. So now on the opposite side, which is going to be now, what is the force between these two, right? So this is the superposition component. Well, the values are the same, right? Now, the only thing is, you know, Q3, notice it's negative. So that means that my force is going to be attractive. So this is going to be in this direction. All right, so if I would be drawing this out, so if I would take this, well, I can draw this out, and it's going to be actually now in this direction, but it's going to have exactly the same magnitude, right? So that's what's going to happen. So now, if this is 64.7, etc., so is this. This is going to be 64.728. Now, if you don't believe me, you can certainly plug it in, but the numbers are the same, right? So what I mean by the numbers is that if you take the formula altogether, right here, so this was Q1 and Q2. Now, if you substitute instead and you put Q3, so this is, you know, the actual force caused by Q3 on Q1, well, the magnitudes are the same. The distance between them is the same as well because of the fact that we had these. Now, if they weren't the same, we would have to find it. So it'd be a little bit annoying, but that's what we would have. So this is a, you know, basically a symmetrical problem. And then, of course, the constant's the same. So I don't have to compute this at all. And I will have exactly the same value. Just now notice the direction is different. And now, so how am I going to break this down in here? So if you're looking at this overall, then what you have, so with respect kind of to this being the horizontal, okay, so I'm going to just put this as a horizontal line right there. Okay, so that's what we have. I've already, let me just delete this, kind of these arrows in here. Okay, so that's, we know what the value of that magnitude is, and then we know what the value of this magnitude is. Okay, so great. So now, how are you going to find what the result is? Well, you have vectors. So basically, what you have to do now is utilize trigonometry. So for this vector, you're going to have to find the y component and the x component. And for this vector, you're going to find the y component and the x component as well. Now, we know what the angle is. So this is 45 degrees. This is 45 degrees because of the fact that it's nothing else except that the distances are the same. So how do I know it's 45? So notice, take a look here at the triangle, right? So this is equal to 1 centimeter. This is equal to 1 centimeter as well. And if you remember, so if you wanted to find what the angle is, well, the angle is nothing else but, so this is going to be, I'm going to put 10, okay? Sorry, 10 of the angle is 10 of the angle is opposite over adjacent, right? But this is just 1 over 1. So this is 10 of the angle equal to 1, which means the angle is equal to 10 inverse of just 1. And, you know, I hope you don't need much convincing. You can just double check for yourself. That's going to be 45 degrees. So now that I know that, I can break down each of these vectors, okay, that I have. The one thing that I will not need in here, so although you can do it, right, you can find out the vertical components, But notice, because these two vectors are the same, exactly, and they're both at 45 degrees, this, okay, component of y and this component of y, they're going to cancel each other off because they're going to be identical, right? And then the x component right here, because it's 45 degrees, okay, so you're going to have one, which is coming from this, and you're going to have another one, which is coming from this. So you have two of these same components. Now, if you do that within here, so let me kind of go back in here. So that means the x component of the force is going to be, so this is going to be the x component, which is 64.7, 28 newtons multiplied by, this is going to be cos of 45 degrees. Now, so cos of 45 is just 1 over square root of 2. Okay, so you can check that for yourself, or you can just go ahead and utilize the calculator. I mean, we have everything here, so it's going to be that multiplied by, so let me just take cos, okay, of 45 degrees. So that is the component that I wanted, right? So this is in the x direction, etc. Now, that's coming from one of these, and it's also going to be coming from these, right? Because if you project both of these, they're going to be aligning, okay, in this direction. And there's two of them. So that means this, you just have to multiply now by 2. So since I already have it, I'm going to multiply this by 2. And you will have your, so this is 91.5. I'm going to just keep it to 3 significant figures, okay, in here. If you want to round it to something else, you can. And that would be the resultant force on Q2. So again, the y components, so going up and going down, they would be actually identical to the x components in magnitude, but they're going to be in two different directions. One is going up, one is going down. So they'll cancel each other off. So what that is telling us, that this particular result, so coming from here, basically that's going to be our overall vector, so 91.5 newtons to the right. So that would have been the result for this example. And that is it. All right. So it's a fun example because it utilizes trigonometry, okay, that you have it, and utilizes Coulomb's law. Okay. I hope that you found it useful. You can post any comments below. Happy studying. Bye, everybody.